Okay, so now it should be correct.
Professor, the module 1 is not posted and it's also locked still.
Okay, so I'm going to differentiate between organic chemistry and inorganic chemistry. Inorganic chemistry would be what you in 305. 306, we're going to be doing organic and biochemistry. And that's specifically, if you look this up, it's the study of carbon-containing compounds. Okay, but it isn't just carbon, it's sulfur, nitrogen, oxygen. Those are the three additional, and sulfur actually too. Usually studied in organic, and there's quadruple, there's a whole bunch of different combos of those. I mean, a whole bunch of different ones. When you take 420, which is the year-long organic chemistry, no biochemistry, just organic, you get into lots and lots and lots of variations on that. Okay. There's a lot more organic compounds than there are inorganic. This is more than 6 million. It's probably more like 20 million. More and more of these things are being generated all the time, much more so than inorganic compounds. You have all the new drugs and all the new pesticides, and just goes on and on and on with organic compounds. In general, they differ quite a bit, organic versus inorganic. The bonding is usually covalent with organic. Usually it's ionic with inorganic. Forces between molecules, we're going to study that a lot, which is called intermolecular forces. They're generally weak with inorganic, quite strong with inorganic. I mean, it's just whatever one is, the other is the opposite. Solubility in water is low. Inorganic stuff, it's very high. When it says often, that means there are exceptions. For example, solubility for organic compounds, if you have an organic acid, for example, those are pretty soluble in water. But those are the exceptions, though. Frequently, they don't conduct electricity, and the rates of reactions, again, usually meaning their exceptions, are slow. However, TNT is an organic compound, and its reaction is extremely fast. TNT stands for trinitrotoluene, and it, as you know, is an explosive. It blows up really fast. So there are a lot of exceptions to these. But in general, these are kind of the generalities between organic and inorganic. Bonding. Now, bonding is usually covalent. Here's a ball and stick model of propane, of 3-carbon alkane. And these carbon-hydrogen bonds are all covalent, meaning they share. So we talked yesterday or Monday about Lewis dot structures. And if we're going to do a Lewis dot structure, this guy here, for example, it would look like this. That would be the Lewis dot structure for propane. Now you're going to be learning how to name these organic compounds very shortly. You're going to have to memorize a series of mono, di, tri, tetra, penta, etc. For naming. But this would be a Lewis structure for propane, and this would be the line drawing for propane. Much more simple and quicker to draw. And I'm going to be talking in detail how to do the line drawings. And actually part of your lab 1 is doing the same thing. And one thing about organic compounds, because they can be quite complex, we can have something called isomers. There's various types of isomers. The kind we're going to be studying in this chapter are called structural isomers. Now, an isomer has the same formula. This is what I showed you yesterday on the ethanol, ethyl alcohol, drinking alcohol, and the dimethyl ether. Those have the same formula, hence they're called isomers. So that's an important concept to understand because we're going to be hitting this time and time again in the units. Okay, now there are a number of non-carbon units attached to carbons. In fact, all the chapters talk about those, and these are called functional groups. For example, up here, one of the functional groups is an alcohol. Another functional group is called an ether. These all attach to carbon atoms. The only one that it doesn't apply to is alkanes, because those are only made up of single carbon-hydrogen and carbon-carbon bonds. Those are alkanes. The whole chapter is devoted to alkanes. So the alkanes really don't have a functional group attached to them. Now, there are three ways of drawing an organic molecule. This is the worst because of all the hydrogens. This is bad too because it has the least structural information. The best kind are line drawings. Now, your book does a nice job on explaining how to do that. I'm going to have a whole sub-unit on how to do that today. So that is the way we're going to be doing our organic molecules. So for this molecule up here, it's got 1, 2, 3, 4 carbon backbone. That means that is butane. To draw that as a line structure, I always say 1, 2, 3, 4. So that's what butane looks like. Notice there are no C's and no H's. The H's are implied, and the C's are at the start, in the beginning, and every time there's a crook in the line. And again, I'm going to go into this a lot more detail in a minute. Alkanes are also called saturated hydrocarbons versus unsaturated. Now, the unsaturated ones are chapter 13. Chapter 12 is on the saturated ones. Now, you'll frequently hear that polyunsaturated, saturated fats. That has to do with the chain on the fats, the long carbon chains on the fat, whether they're saturated or unsaturated. And we're going to go into detail into that when we get to the carboxylic acid chapter. Now, what's important is we are not going to cover triple bonded carbons. And the reason for that is because in your body, there are no triple bonded carbons. And you are in an allied health track. So there's no point in covering stuff that you're never going to see the rest of your life. Our bodies have a lot of single and double bonded carbons and also aromatics. So that's what we're going to focus on. Now, alkanes can be represented with this general formula. So say we have a 3-carbon alkane. That means we automatically know how many hydrogens there are, because 2 times 3 plus 2 is 8. 3 times 2 6 plus 2 is 8. So that's the number of hydrogens. Okay. Alkanes go from 1 carbon up to 1,000,000. The simplest one is called methane. That's its formula. Methane is usually a main component of natural gas. It has no odor. So to prevent accidents, what they do is it's called odorizing the gas. They put a stinky molecule in there so that if you have a gas leak, you can smell it. And it's a sulfur compound. Our noses are very, very sensitive to sulfur compounds. For example, what makes a skunk smell so bad are the sulfur organics in there. Frequently, you use propane for your barbecue. You can use butane, which is a 4 carbon. 4 carbon alkane, and that butane is used, like, for example, in lighters and stuff. Okay, so those are the simplest alkanes. Now, one of the things about organic molecules is carbon has 4 bonds, and whenever that Monday, big time. So carbon can bond to another carbon or an oxygen or a sulfur. When it's bonded to another carbon, we have something called a branched alkane. If it's not bonded to another carbon this way instead of a hydrogen, it's called a normal alkane. Basically, they call these straight chain. Versus branched. Now, this is going to impact how you name these molecules. N-butane, N stands for normal. That means it's straight chain. So when we say N-butane, we're going to get to what the buta means in a minute here. N-buta means 4 carbons long, no branching. And then there's various ways to show how branching is represented. One way is naming the iso group. Another way is, I'll show you in a minute here. Now, single bonded carbon-carbon bonds freely rotate. What they do is they freely rotate and end up in the most stable position. So right now we have, this is called a methyl group. Right now we have the 2 methyl groups on top of the carbons. This is least stable because it's something called hindrance. The methanes are buttoned up against one another. Nature does not like hindrance because it raises the potential energy. You raise the potential energy, that is less stable. So what happens is this twirls around so that the methyl group is on the bottom. This would be the most stable. Now this one here is more stable than this one, but this is the most stable because the methyls are as far apart as possible. That's what this here is, okay? So here the methyl groups are coming up from the carbon and they're next to one another. So least stable.
Oh, wait, no. I'm like Zoom. Yeah, I put it in there.
He was like. So
yeah.
It
It was amazing. It was I can't even explain it. It's really nice. Like I feel like I've been waiting for that for like hella long.
Hey guys,
Yeah.
there's a bunch of
Yeah.
people that are unmuted.
And then
Just
I met up
FYI.
with one of my nursing classmate that was there, and then I was like, "Oh, take a picture," but we were too excited to see each other and shit. And my plan was to like grab a drink with her,
You're unmuted.
but I was like so excited. I just like
You guys.
by after taking a picture.
Like,
You
in
guys,
that way
I
that
can
was
hear-
kind of
Like,
like,
totally-
You guys,
I totally didn't
hello? I can hear
relax,
all
but,
your
like,
talking in the
sexy.
background.
okay, I was like, okay, cool.
Yeah, it was lit.
Nick texted me.
Everyone,
Nick just
everyone.
texted me.
please mute.
What? No,
I
I
can
said,
hear
"Wait,
everyone
didn't get that
talking.
phone.
Report, yes.
Go to school, you know?
I got my
Right.
S4 right.
Um,
Ah,
um.
students. All right, everyone, mute, please. Chit chat all you want, but just don't have it turned on.
But I
All
can
right.
run. You saw.
So the problem is,
You guys all leave. Right?
Mhm.
I'm sleeping over with just the two.
I
can't.
You
One
just
Spicy
went.
tea.
Mute.
Right, it was wonderful. And in my head, I'm like,
It's like
I'm a
that,
wingman.
and then I believe
Like,
that I believe that
I-
it's getting cut up. So
I think you can mute.
Professor, that you can mute them. Malia like
I'm dividing my attention.
We're all brushing our teeth.
I'm dividing my attention.
Malia comes.
everyone, mute. M-U-T-E, please. I hear everyone's talking. Okay. It was wild. All right, so let's go ahead and continue here. Now, one of the challenges with alkanes is, as I was mentioning up here, these carbon-carbon single bonds can rotate. So if we look at this molecule here on the top left, we have 1, 2, 3, 4, 5 carbons. Okay, and there's no branching. This one here, we have 1, 2, 3, 4, 5. So these are the same molecule. That means the name for both of these is the same. It is N-pentane. Okay, now look at this here. This on the bottom left, we have 1, 2, 3, 4 carbons, and we have a branch here. So this, the longest carbon chain is 4 here. Up here, it's 5. Call that the backbone. Here, it's a 4 carbon backbone. Hence, the name is going to be different for the 4 backbone versus the 5 backbone. It has the same number of carbons, though, 5 and 5. But what's different is the backbone here is 4 carbons with 1 carbon sticking out on number 2 carbon. 1, 2, 3, 4 on the bottom right. That means that is also a 4 backbone. Now, what you're going to be doing when you're naming these things is you're going to be finding the longest backbone. So you can count this a lot of different ways. We can go 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Any way we number it, it's still 4 carbons with 1 carbon as a branch. So this is also a 4 carbon backbone. Okay, so this is a big deal. Straight chain versus a branch. Because the branching is part of the name. So it's important to be able to identify right off the bat, what is the longest backbone? Number 2, are there any branches? And number 3, what is the functional group? Every time we get to a new chapter, we're going to be talking about those 3 parts on naming. Now, this first chapter, you've never seen this before, unless you're repeating the class. Never seen this before, so it's kind of awkward. Okay. Let's look at this. What is the longest backbone on the left molecule there? 1, 2, 3, 4, 5, right? One, two, three, four, five. Okay, they both have 5 carbons, and the longest chain is 5 in each one. So that means the name of these two molecules is pentane. It's the same molecule because the carbons can twist. Okay, so let's look at this now. 1, 2, 3, 4. 1, 2, 3, 4. That's the longest chain. So both of these have a 4 backbone. Now, these are called structural isomers. Isomer means it's the same formula. Structural means the only difference is the carbon-carbon bonds are just twisting around. It's the same molecule though. Now we're going to find in chapter 13, chapter 13, when we get into double bonded carbons, those cannot freely rotate. So you end up with different kinds of isomers. Now, you have to name the backbone. So you name the branches differently than you name the backbone. That's why it's important to identify what's the backbone, what are the branches. Now, these guys here need to know. And when you get into a naming problem, we're going to go over lots of examples of these, but these you need to get to know. I'm going to go over them. And then you can also have these as branches as well. So these are the branches. Continued here, branches. And these are branches as well. So all 3 slides, you've got branches. Okay, so that acronym there, IUPAC, stands for International Union of Pure and Applied Chemists. That's an international standard of naming stuff. And like I was saying before, you've got the prefix. That's the branches. Denotes longest carbon chain. That's the backbone. And then this is the functional group. Okay. So you need to know this. Meth, F, prop, but, pent, etc. Up to 10. Okay, so let's do an example. First thing I want you to do is, let's see, I've got all the. Okay. Number one, identify the longest carbon chain or backbone. That would be this here. Also, you could say, yeah, both of those are 5 carbons long. Both are valid. Most of the time, students feel the yellow one is more obvious than the green one. But remember, carbon-carbon bonds, single bonds, can freely twist. So these are the same backbone. Next thing, so let's remove the green one for now. And just look at the yellow one. The next thing you do is, are there any attached carbons to that longest backbone? Different color. Let's use blue for that. Okay, so we've got, oops, what did I do?
Oh, y'all do know it.
Most of my students like to use highlighters. You don't have to, it makes it easier. Okay. So we've got, and there's 2 ways to number this. You start on the right with carbon number 1, or you start on the left with carbon number 1. You have to number it both ways. So if we start on the right, the branch is going to be in carbon number 2. If we start on the left, the branch is going to be in carbon number 4. The branch is 1 carbon long. That means it's a methyl. That's what this means. On carbon. Pentane means it's 5 carbons. Now you have to specify where the branch is located. So it depends on how we count. One way we count the methyl branch, the blue branch, is on carbon number 2. The other way, it's on carbon number 4. So based on how you number it, you can get these 2 names. And which one's correct? The one with the lowest number. So that one's the more correct one. Now in a test, if you put 4-methyl pentane, I would probably take off a point or something like that, because you have the idea right. You just didn't do it totally correct. That's why I don't do multiple choice. You can have multiple branches. Let's look at this molecule here. Okay, longest chain. Let's count here. Well, we can go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, it looks like 7 is the longest chain. So, like up here, yellow is in their backbone. Over yellow. Okay, and now we have a number of carbons off the backbone. So those go in front. So this is the backbone. Seven carbons. And all this other stuff, the blue stuff, we have to specify. Now, if we start numbering from the left, we'll get lower numbers as opposed to numbering from the right. So we have methyl, methyl, isopropyl. These are those branches I told you that you have to know up here. These are the branches. So this is the one, the isopropyl. The other one's methyl. So we have two methyls. That's going to be a dimethyl. And we have one isopropyl. Okay, we have to say where the carbons are located that the methyls come off of, carbon 2 and 3. 2, 3. How many are there? Two of them, dimethyl heptane. The isopropyl comes off of carbon number 4. So which do you put first? The isopropyl or the dimethyl? Now you would think you put the dimethyl first because D comes before I, but you don't consider the di part of the branch. It's just how many. So really it's an M. So really it's methyl. So M comes after I, so that's why the I is first. Now this takes lots of practice. Lots of practice. Okay, so any questions about what I just did, either up here? First of all, are there any questions about this one?
Professor, I just have a quick question. I was wondering if you would be able to post these slides to Canvas.
Yes.
Okay.
Also, I don't think you uploaded the recording from Monday on Canvas. Like,
I
we
did.
can't.
I did. Go to modules.
I did, and it's not on there. It just shows the administrative module.
It's on pages.
Okay.
That's what I did when I first started the video today. I went on to student view of Canvas, and I actually clicked on the video and it actually started. So it is there.
I think she's saying is that the module itself isn't posted. Like we could see the video if you go to pages, but there's no modules after administrative module.
If you go down to unit 1,
Yeah, the unit 1 module isn't there. It's just administrative module.
okay, chill out. Let me just stop here. Okay, so we have administrative, lab related, unit 1. Are you not seeing that?
No, we do not see that.
Yeah, see, the unit 1 isn't posted. The video is green, but the unit itself is not posted.
Try it now.
It's on there now. Thank you.
Okay, while I'm on Canvas, what I'm going to do is I will always have the slides available. And let's see. Let me do it right now. It's a big PDF, can you tell? Okay. So it is officially right here. Okay. So would you like a few minutes for you guys to download that? Or do you want me to just continue on? Okay. Is it possible to pause for a few minutes so we can process the content? Yeah, let me give you some practice problems. And would that help? And then we can go over them.
Yes.
Okay, all right. Now this is totally new to you guys, totally new. So every class I've taught, and I've taught like 48 of these, this is a real stopping point. They'll all go, are you kidding me? There's a lot to do. Now we're gonna be doing naming in every single chapter. Every single chapter. The biochem chapters, naming is different than organic, but it's still naming. And all the organic chapters are going to be using the same naming convention and branching and all that stuff. Also, I will post a number of worksheets for practice under Unit 1. And also our Lab 1 is going to practice not naming, but going from formulas to line drawings, etc. So we have a lot of repetition here. And that's the way I learn, is for me, I don't memorize things very easily. I have to do it over and over and over and over again if I memorize it. And even then I have to keep practicing, otherwise if I don't keep practicing, I forget. That's what happens when you get old. Okay. Okay, so no one mentioned they wanted some time to download the slides. Is that correct?
I actually had a quick question regarding the second problem that we went over.
This one here?
Yes, the
Okay.
longer one. So I understand how we find the backbone and how we identify the branches. The naming part, for the purple 2,3-dimethylheptane, that part is kind of confusing to me. I'm trying to go back and forth between the slides to find the names. So you
Yeah.
could go over again of that part.
Yes, so if you print off this one and this one, those are very, very, very helpful. So after we're done with this lecture, go ahead and end lab for those of you who have Wednesday lab, but the Monday lab people have some time. Print these off. These will be very helpful for you. Particularly this one here. This, when you get into the 4-carbon branching, it gets a little tricky. Then there are these guys as well. The main one on this one is going to be chloro. Right here, chloro. And nitro and amino. Those are the 3 that are really important. The rest of these will not, particularly this one, we will never run into in the body. In fact, any of these really. But the chloro, we will on products we ingest. And hopefully we don't ingest any with chlorine, which is not good for you. Lots of nitros and lots of aminos. Okay, so let's do a practice one here. Now I'm going to post all the slides before I lecture. I was doing this just before lecture. I was getting this all together because the publisher did not furnish me any slides for your book, fortunately. That's why I had to go back to another book. But I do have the slides ready for you for chapter 13, 14, 15, etc. Okay, so I'm going to post those for you. So you can print these off if you want before you hear me lecture on. That should help. Is that a fair statement?
Yes.
Don't everyone answer at once now. Okay, so let me do the line drawing for these 2 while we're doing it here. Okay, so first thing, you find the longest backbone. In this case, it's going to be 5 carbons. So we need to do the line drawing 5-carbon branch. So what you do is you start at the first point. That's going to be carbon 1. So you're going to go 1, 2, 3, 4, 5. So that's the carbon backbone in yellow. Next thing is we need to do the branching. And we have a branch on carbon number 2. That's right here. So that's what the line drawing looks like. Now the other thing is, let me do this a little differently. If we started over here on the right, 1, 2, 3, 4, 5, then the branch is going to be on the second carbon, which would be right here. So those 2 are equivalents. One is just flipped in the air. So you have your backbone, and you have your branch. Let me do this one. 7.
Professor?
Yeah.
You said both those options would be correct, right? Not just one of them?
Here?
Yeah.
No, only the top one.
Oh, okay.
The reason why the top one is more correct than the bottom one is because the numbers are smaller.
Oh, okay.
See, two smaller than 4.
Right. Okay.
That's all the math we're doing in this class, by the way. No stoichiometry, no dimensional analysis, no conversions from Avogadro's number to whatever. None of that. We're just doing real simple stuff. But this is where the trickiness of this class comes in, is things like naming, and when we get to reactions, it's going to be another interesting challenge. Okay, so does that make sense why 2-methylpentane is more correct than 4-methylpentane?
Yes.
Okay. Now, had doing this one, you might have put the 2-methyl. Okay, so you might have done this one first, thinking the D is less than the I. But the DI just says how many methyls. So really it's an M versus an I. That's why this one's more correct and that one's not. But again, if you put this one on the right on a test, I would still give you lots of partial credit. I wouldn't say it's, I would take up, if it's worth 10 points, I'd take off 1 point or something like that. Okay, so let's do some practice problems here. Okay, the best way to do this is have this screen available. Okay, so I'm going to do, I'm just going to write C's rather than all the H's. Okay, so that's one. Remember, there's H's all the way around. Let me do the line drawing version of that. And then let's do, and this would be the line drawing. Okay, go ahead and do those.
I have a question.
So do backbone first, see if there's any branches.
Okay.
What was your question?
I was just gonna ask why when you do the line drawing, why is it like the backbone, the other ones, why are they in a different side?
Different sides. Remember, the carbons can spin. Carbon-carbon single bond can spin. So all those three are the same.
Okay.
Now see this can spin.
Okay, gotcha.
That's when you first start doing this, that's tricky. And I think next week I'm gonna get some model kits. So you can actually build these and then twist them yourself in your hands. You can see it better.
So when we're drawing the line graph, why is there like a correct version to do it then? Like the single ones?
The line one we can twist as well. For example, we can go like that and like that.
Okay.
Exactly the same thing. We're twisting. Remember, this is carbon, 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 carbon. So that means carbon. So this can spin here. So at the end of the line drawings is a C. Every time there's a crook in the line, there's a C there. So there's C, 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 C.
Okay, got it. Thank you.
But, if I had to put H's in all this stuff, what a pain. That's why organic chemists have only use the line drawing. You will never see the CHs in there. Except for chapter 1, when they teach you how to do line drawing. Now, you guys are doing these practice problems right now, right?
Yes.
Okay, that was the intention, yeah. Give everyone another 4 minutes, then we're gonna go over these.
Professor,
Yeah,
are there two separate problems on the right of the screen? Are those two separate ones?
yeah.
Okay. I mean the ones like on the top right. Are there two there?
No, that's just different ways of writing this, and this are the same thing.
Oh, okay, I see. Thank you.
Yeah, and the reason why they're the same is because those carbon-carbon single bonds can twist.
Right. Right. Okay, thank you.
Sure.
Hello, Professor. I have a
Yeah.
question.
Yeah.
Are we meeting in person for lab today?
Wednesday group is yes.
Yes. And do we need our safety lab equipment?
No, because I'm just
No.
talking about, I'm actually talking about safety lab equipment. I'm going to show you a movie on safety from the American Chemical Society. And I'm going to talk about a couple things you need to your first labs. And also want to talk about the lab write-up. That's what we're going to cover today. It won't take the 3 hours. It'll take an hour and a half.
Okay, thank you.
Sure. Okay, one more minute. Okay, so let's talk about these. All right. I'm going to erase. These are all the same. Okay, first thing we're going to do is identify the backbone. 1, 2, 3, 4, 5. Next thing, are there carbons off the backbone? Yes, there are. Okay, so a 5-carbon backbone is a pentane. And let's see, where was that? It was, there's a listing of all these. Right here, 1 through 10. So here we are, penta. So pentane is the backbone. And do we have branching off the backbone? Yes, we have 2 methyl groups off the backbone. And what are those carbon numbers where the branches appear? Well, it's on carbon 1, 2, 3, 4, 5. It's on carbon 2 and 3. And how many are there? 2. So that's di. So it is 2, 3, dimethyl pentane. We're doing the same thing down here. There's the backbone. And here's the 2 branches. Does that make sense, you guys?
Yes.
Yeah. Yeah.
How do you know it's a pentane?
Count the carbons on the yellow backbone.
Okay.
There are 5. That's where the pent comes in. And because it's an alkane, we're going to use pentane, T-A-N.
Got it.
Okay, let's look at the bottom one now. Okay. Longest chain is, we can either go straight across or up to the 4 carbon and then down. Okay, so that's 6. That means that's a hexane. And then we have branching off of the yellow backbone. We have 2 of them. Now, one is a 1 carbon and the other one's a 2 carbon. So one's going to be a methyl. Oops. That's one carbon, and the two carbon is going to be an ethyl right here. Okay, so which comes first, the ethyl or the methyl?
Ethyl.
Ethyl, cool. So that's two ethyl. Actually, it's not two, it is four, not three. Four ethyl, two ethyl.
And that's 4-ethyl because it's on the fourth carbon, right?
Exactly, exactly.
Can you explain why does the ethyl come before the methyl?
Alphabetically,
Okay, thank you.
E before N, alphabetically. Now, if it was a diethyl or a dimethyl, the di-tri part is just doesn't count in the alphabet. That just says how many of them. So the main letter to focus on would be the methyl, ethyl, propyl, whatever. Now, do these examples help?
Yeah. I just have a quick question. So numerically, it would still be 4-ethyl because we're numbering from where the first functional group comes off, which is methyl, correct? Like, so methyl would be the second one, right? And then ethyl, yes, would be the fourth, but I had put it where it was 3-ethyl, 5-methyl because I got confused between the alphabetical ordering.
Okay, so let's do it the other way. Let's number from, let me reproduce all of that. Let's see how this way to do that. Let's see. Okay, but what if you numbered from the right side? We have carbon there, and like that. Is that the way you numbered?
I still numbered it the same way, but I just thought because alphabetically came before M, that's why I had suggested that it would be 3-ethyl, 5-methylhexane. But I get what you're saying as to why it would be the other way.
Okay. Because if we, let's just say we numbered from the right going to the left, that would end up being 3-ethyl, 5-methyl. Okay, so we have, again, this fancy math. We have 4 plus 2 is 6, 3 plus 5 is 8, which is less the top one, because that's 6 versus 8. That's why the numbering on the bottom is incorrect, because it gives higher branch numbers.
I see. Okay, so you want the lowest branch numbers and then in alphabetical order.
Yeah, so once we decide the top one is the right one, then which one comes first, the ethyl or the methyl? Then it's the alphabetical order.
The ethyl does alphabetically.
Yeah, exactly. And that's why it's first for the methyl. Even though the number's higher.
Are we able to do one more example?
Sure. Let's see. Best way to do this one. 'Cause I want to leave this here. All right, I'm going to erase the first one. Do the other example right here. Okay. Yeah. And, do the same thing, identify backbone first, and then are there any carbons off the backbone? Is your name pronounced Selah? Selah Pons?
Yeah, it's Sayla.
Okay. Do you see why it's not isobutyl on the second one?
Yeah, I saw that mistake after you went over it.
Okay. Yeah, because butyl means there's 4 carbons. There's only 2 there. Okay, so let's go over this. First thing, identify the backbone. So it looks like the backbone, the longest one is probably in the middle there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So this is the longest right there. Okay, so now we have 3 branches. Carbons off the backbone. Right there. Okay, so 6 carbons is hexane. Now we have 2 methyls and 1 ethyl. So if we number from left to right, we're going to get the lower numbers than if we start with one from the right to the left. If we start on the right, we're going to end up with the first methyl at 3. We start on the left, the first methyl is at 2. So that's the better number from left to right. Okay, so we have 2 methyls and 1 ethyl. Now the ethyl comes before methyl, and that is on carbon number 3. So that's 3 ethyl. Then we have methyls, the 1 carbons on 2 and 4. So that's 2, 4 dimethyl hexane. Okay, the line drawing will look like this. We have methyl there. And we have a.
I have a question.
Sure.
So di or D is before E in the alphabet. A, B, C, D, E. So wouldn't it be dimethyl first?
No. Yeah,
Why?
the di just says how many. So it's
So that doesn't count as like the alphabetical part of it.
exactly.
Okay.
That's just counting. The part that counts is the M in methyl.
Okay. Got it.
Okay, is this starting to sink in a little bit? You need
Yeah.
Yes.
lots of practice, though. Okay, so let's just zoom along here. Now, another interesting aspect of organic molecules, they can be cyclic. So you have to, in your naming, you have to say it's cyclic. So for example, if we had okay, now if there's a cyclic component to that, that automatically becomes the backbone. So automatically, that's the backbone. And it's 6. So it's going to be cyclohexane. Okay, it could be cyclopentane, cyclobutane, cyclopropane. And is there a branch off the backbone? Yes, there is. Right here. And that's a 2-carbon branch, so it's ethyl. So numbering on cyclocompounds, usually where the branch is carbon number 1. Now we're going to see in the next chapter, it varies, and then you have to count it a couple different ways. But in this chapter, when the branch comes off, that's carbon number 1. So we have 1, 1-ethyl cyclohexane. Okay, so what if you have multiple branches off the cyclo? Okay, so in this case, we have, now it's easier to draw this like a house. Okay. So this has a branch going off there. And a branch going off there. So we do the backbone because it's automatically cycle. And we can name this one of two ways. So what's carbon number 1? Well, we have to name it 2 different ways, see which has lower numbers. So So 1, 2, 3, 4, 5. So if we named it, numbered it this way, we'd have 1-methyl, 3-ethyl, cyclopentane. If we numbered it up here as being number 1, and then coming towards, clockwise, towards the methyl group here, it would be, oh, wait, is this right? The order?
Ethyl has to be first.
Yeah, these need to be swapped because E comes before M. Okay, if we did it the other way, starting with 1 up here in the, let's say I'm gonna do it in a different color. Let me show it really well. So now it's going to be 1-ethyl. Methyl, cyclopentane. So 1 plus 3 is 4. 1 plus 3 is 4. So as far as this classing is concerned, those are equally as correct. Because when you add the numbers up, they're the same.
So basically when you're numbering, should you start like 1 on like the branch or the branches, like either one?
Yeah.
Okay.
Or if there's a functional group there, we're going to see in a couple chapters, if it's a functional group coming off that, that dictates what carbon number 1 is. Alkanes have no functional group, they're just H's. So it's a little dicey sometimes how you count. Okay, so on a test, these would both be fine, assuming you put the ethyl first.
Does it matter if you count clockwise or counterclockwise?
Say again?
Does it matter if you count clockwise or counterclockwise? Because I see you went both ways.
No.
Okay.
You were hard to understand, so I think I understood what you're saying. Okay. Now, as I specifically set up above, carbons, single bonded carbons can spin, rotate. However, when we put them in a cyclic configuration, we have rigidity, and they cannot freely spin or rotate. So we can have something called geometric isomers. So both these are 1,2-dimethyl cyclopentane, but they aren't the same molecule. If they're on the same side, remember, these are rigid now. These two cannot go back and forth because it's cyclic. As soon as you have cyclic, you have rigidity. The carbons cannot move and spin around like they can if it's non-cyclic. Okay, in this case, if they're on the same side, it's called cis. If they're across from one another, it's called trans. So we have cis 1,2-dimethyl cyclopentane, trans 1,2-dimethyl cyclopentane. Okay, and that's only if it's rigid. Now, when we get to the next chapter, we're going to find double bonds carbons are also rigid. So you can have a cis trans with double bonds again. So this is your first introduction to cis trans. Now, I'm sure you've heard of fats. You have cis fats, trans fats. They never mention cis fats. They always talk about trans fats. And that has to do with the fact that in a certain fats, there's a double bonded carbon along the long fatty chain. And then because it's a double bond, we have rigidity, hence you can have cis and trans isomers. The natural isomers in our body are cis, not trans. So when you introduce a trans fat into the body, it's abnormal. So when our body tries to metabolize it, it doesn't do it the right way. It messes things up. So that's why you should stay away from trans fats. Whenever you have deep fat fried foods, frequently you'll introduce trans fats into your foods. That's one of the reasons. Just try to not eat deep fat foods, although they're really good, very often. Okay, so again, the key word is rigid. Rigid. If the carbons are rigid and can't freely rotate, look for cis-trans isomerism. Okay, so we're finished with naming. Alkanes are very nonpolar, meaning they don't dissolve in water at all. That's called hydrophobic. Typically, they're less dense in water, hence they float. As the size of the molecule increases, melting and boiling points go up. So methane has a very low molar mass, hence it has a very low melting and boiling point as opposed to butane. And you can, that's illustrated here. Let me make that bigger. As the number of carbons goes up, so does the melting point and the boiling point. Density changes a little bit. That's because the bigger the molecule, they can fit more compactly into one another. You can look at it on a graph for the number of carbons versus boiling point. If this is room temperature, you can see methane, ethane, propane. As it goes up, as soon as it hits pentane, it's transition between a liquid and a gas. So for butane here, it's easy to make it into a gas or into a liquid because it's really close to being a liquid here. Okay. Now, in every test, there will be naming, IMFs, or did you go over IMFs, intermolecular forces, in 305?
Yes.
Okay, so I'm going to review them, but every test will have naming intermolecular forces in 3 reactions, every single test. This is the one that most people have challenges with, reactions. Now, for alkanes, there are only 2 reactions. One is combustion. They burn like heck. Gasoline, diesel, coal, methane, ethane, butane, propane, they all burn really, really well. And they produce, assuming there's enough oxygen present, they all produce carbon dioxide and water. Unfortunately, carbon dioxide, which is a greenhouse gas, but they all produce same thing basically. So, oh, and then the other reaction is it's called halogenation. In other words, you can add a halogen to an alkane under heat and light. So we are going to be working with that, not fluorine and bromine or iodine. So this represents the alkane, the CH. So we introduce the halogen, which is like Cl2. What's going to happen is this is going to be with a Cl branch somewhere along the molecule. But you have to have lots of UV and or lots of heat or both. So those are the 2 reactions. So if you have, let's say, pentane plus O2, you end up with carbon dioxide and water. Say we had propane plus Cl2 with heat and UV. You'll end up with we get a mixture. It'll either go in the middle or on the end. So those are the 2 reactions for this chapter. Now, if you remember, sometimes you'll have the CO2 over the arrow, doesn't matter. Either one of these is fine. And then halogenation usually yields a mixture. Depending on how long the backbone is, it'll add in various places. Some places are more stable than others. For example, let's go back up to here. Between these 2, which do you think is more stable? This one or this one, top or bottom?
The bottom with the top one.
We have a mixture, right? Okay. Nature likes symmetry. So which do you think is more stable, the top one or the bottom one?
Top one.
Top one is more symmetrical than the bottom one. So that would be, so you'd end up with a greater amount of that than the bottom one. Now, we're going to have reactions throughout the semester where we have mixtures. That's frequently the problem. And you're going to be circling the one that is most stable. And there's some rules going to be going by as we go along further in the chapters. But basically, symmetry is a very strong stabilizing agent in the universe. So in this case, the top one is more symmetrical than the bottom one, hence it's going to be more stable. Okay, so that's it for chapter 12. We went over reactions, not very many. And we talked about naming. Why there's spots here, I took out some very obtuse slides that aren't all that relevant to our course. So. Okay, so we have a little bit of time left. So let's do some more naming practice. Don't forget about whenever there's rigidity, think possible isomers. Not always, but possible. Okay, let's do a couple up here. And now, the lecture is officially over. So if you'd like to stick around, I'm going to go over some more examples. You're more than welcome to leave or stay. Okay, so let's do another naming. Let's do one from the line drawing only. Okay, go ahead and try doing that one. Oh, in fact, let's.
Is that a D or CL?
CL, chlorine.
Okay, thank you.
Okay, let's go over this guy. All right, first thing you need to figure out is longest backbone. Okay, so we have, that'd be one option. That's 1, 2, 3, 4, 5. Another option would be 1, 2, 3, 4, 5. Oh yeah, 1, 2, 3, 4, 5, 6. So 6 is winning so far. So that's going to be the longest backbone. So that means we're working with a hexane. Okay. Now we have three branches. One of them is going to be chloro. So let's see on our counting. You can count from left to right or right to left. Looks like we start from the right going left. The numbers are going to be more than the ones starting on the left. So we're looking at okay, so we have a 2-chloro. We have a methyl here on number 4. And ethyl on number 3. Okay, so we have an ECM. So M is highest, C is lowest. So we're going to put the 4-methyl here. Ethyl goes in the middle. Chloro goes up front. For 2-chloro, 3-ethyl, 4-methyl hexane. Now, did you see how I just wrote them out without putting them into next to the hexane and seeing which one would go first, which one goes second? Pencils are really good when you're practicing this with a big eraser. Okay, so any questions about that?
No.
We okay? All right, well, why don't we end today's session? What'd you think of chapter 12?
It was good. Just need some more practicing.
Yes. I'm telling you, you've got to do a jillion of these. A jillion of these. Now, in next chapter, there's gonna be a lot more reactions than in this chapter. So I'm gonna be doing lots of naming, lots of reaction examples. So the other thing is, if we,
I have a question regarding lab.
Yeah.
Do we need to have the written pre-lab part for next week?
no, only wet labs.
Okay, got it. Thank you.
Talking about the lab write-up, right?
Just for wet.
Yeah, yeah.
Okay.
Okay, whenever we do dry labs, just come.
Okay, makes sense. Thank you.
Sure. Okay, so this is where we are today. Here are alkanes. We have the two reactions for alkanes. One is combustion. Producing carbon dioxide and water. We need a spark too. Combustion won't happen unless there's activation energy introduced into the system, also known as a spark. Alkanes can also create a haloalkane, and expect a mix when we do that. And that requires UV and or heat. So we have chlorine gas, which is the only one you need to worry about, not bromine or iodine, anything like that. Chlorine is by far the most common halogen in this reaction. Okay, so alkanes can only, now alkanes can also undergo oxidation. And usually that's at a biochemical level. For example, in the Krebs cycle. We're going to go over that. We talk about carbohydrate metabolism. So there are two main reactions, but later on we're going to see there's really a third reaction. And when we get into the next chapter, we're going to find that if we apply hydrogen gas with a platinum catalyst, we can go from an alkene to an alkane. Now, as you can see, there are lots of reactions here. These are all unit 1 reactions. Okay, I just wanted to show you how convenient this is. All right. So I'm going to end it now, and I'll see you Wednesday, folks, in lab in a little over an hour, I guess. I usually get there early because traffic is pretty good coming from Natomas down to Sac City. Going home is another question, but during the middle of the afternoon, traffic is pretty good. So I should be there around 2:30. So if you want to come early and talk, that's fine. If you want to come early and not talk, that's fine. All right, everyone. Okay. And don't forget, I'm going to post this video this evening or early tomorrow morning.